Lesson 28, Radioactive Decay. Radioactive decay is a process in which an unstable nucleus undergoes change by emitting radiation. Radiation is a general term for anything that can be radiated out of the nucleus. Radiation can come in the form of a particle, or something with mass, or energy, in the form of photon emission. Radioactivity was discovered by accident by Henry Becquerel in 1896. Becquerel placed a rock containing uranium on a piece of photographic paper inside a dark drawer. He found that the paper developed an image as if it had been exposed to a strong light source, even though there was no light inside the drawer. We'll start this lesson by examining some of the common types of radiation. But first, we need to talk about antimatter. Antimatter particles are particles that have the exact same mass as their regular matter counterpart, but opposite charge and other properties. Here's a picture of hydrogen and antihydrogen. Hydrogen is made up of protons, neutrons, and electrons. Antihydrogen is made up of antiprotons, antineutrons, and positrons, which are the anti-electron. If a matter particle comes into contact with its corresponding antimatter particle, the two particles will annihilate each other. Annihilate means their mass will completely turn into energy. The particle will be destroyed. They'll cease to exist. In this lesson, we're going to learn about the 6 most common particles emitted in radioactivity. We'll start with the beta-negative particle. One of the symbols that you'll see for the beta-negative particle is the Greek letter beta, which has 0 nucleons and a charge of -1. But the other symbol you're going to commonly see is E, -1, 0. And that's because a beta-negative particle is really just an electron, with a charge equal to negative of the elementary charge and a mass equal to the mass of the electron, which is 9.11 times 10 to the -31 kilograms. Next, we have the beta-positive particle. The symbol you'll often see for the beta-positive particle is Greek letter beta, which has 0 nucleons and a charge of +1. We could also write its symbol as E, 0, plus 1. The beta-positive particle is a positron, which is an anti-electron, the antimatter version of an electron, with a charge equal to positive of the elementary charge and a mass still equal to the mass of an electron. It's different from a proton because it has a mass of an electron, and it's the anti-electron. If an electron and a positron meet, they'd annihilate each other. Next, we have an alpha particle. The symbol for that is Greek letter alpha, with 4 nucleons and a charge of 2. It's essentially just a helium nucleus, so you might also see it written as helium 4, 2. The alpha particle was discovered before the nucleus was discovered. We now know that the alpha particle is a helium nucleus and not a special kind of particle itself. It's made of 2 protons and 2 neutrons, with a charge equal to 2 times the elementary charge. The neutrino has a symbol that looks like a V but a little more curved. The neutrino is a neutral, tiny particle. It has negligible mass, which means its mass is so small it might as well be 0, and it's non-interacting, which means it doesn't interact as it passes by matter. Next we have the antineutrino, which we write as a V that's curly with a bar over top. The symbol for antiparticles is often written as the symbol with a bar over top, or X bar. The antineutrino is also neutral, tiny, and non-interacting. Finally, we have the gamma photon, which is a particle of light. The symbol for the gamma photon is Greek letter gamma, with 0 nucleons and 0 charge. Sometimes it's written just as gamma. The gamma photon is a high-energy particle of light produced in nuclear reactions. Nuclear equations are written like chemical equations, with the original material on one side of the equation and the resulting material on the other. The two sides are separated by an arrow. Here's an example. We could start with the uranium-238 isotope, which is U-238-92. But as this decays with alpha decay, it becomes the thorium isotope, which has 234 nucleons, an atomic number of 90, and the alpha particle, which is the helium nucleus. Any nuclei on the left side of the equation are referred to as the parent nuclei. Any nuclei on the right side of the equation are referred to as the daughter nuclei because they're what the equation yields. There are a couple conservation laws that will help you predict which daughter isotopes will be produced in nuclear reactions. Recall isotope notation X, A, Z, where A is the number of nucleons found in the nucleus and Z is the charge number. The first conservation law we're going to look at is the law of conservation of nucleons. The sum of all the nucleons, or the A numbers added together on the parent side, is equal to the sum of all the nucleons on the daughter side. Next is conservation of charge. The total charge, or all the Z numbers added together on the parent side, must equal the total charge on the daughter side. The final conservation law I kind of made up. It's conservation of antiness. It will help you out when you're examining beta decay reactions. If a new particle, one that didn't exist before, is produced, an antiparticle will also be produced. Here's an example. In this example, we need to predict the daughter isotope that is produced in the nuclear equation. We'll start with conservation of nucleons. On the left side of the equation, the parent isotope has an A value equal to 14. On the right side of the equation, the A value must also equal 14. So we have our unknown plus 0 plus 0 has to equal 14, which means the unknown must be 14. Next, we look at conservation of charge. Z is equal to 6 on the parent side of the equation. Z also has to equal 6 on the daughter side of the equation. So our unknown plus -1 plus 0 has to equal 6. 7 plus -1 plus 0 makes 6, which means the daughter nucleus must have an atomic number of 7. If you look it up on the periodic table, you'll find nitrogen is the element with atomic number 7. In terms of conservation of antiness, in this equation, a new particle, an electron, has been produced. To balance out the new particle being produced, an antineutrino is also produced. This happens in beta decay. This is an example of beta negative decay. We're going to look at the 4 most common types of radioactive decay, starting with alpha decay. In alpha decay, the nucleus ejects an alpha particle. Remember that an alpha particle is just a kind of helium nucleus. In alpha decay, 2 protons and 2 neutrons leave the nucleus. An alpha particle is this bundle of 2 protons and 2 neutrons, which is a helium nucleus. As a result, the original nucleus is decreased by 2 protons and 4 nucleons. The nuclear equation always takes a form looking like this. X, AZ, the original parent nucleus, yields a daughter nucleus, we'll call it Y, which is 4 nucleons less and 2 protons less, Z minus 2. And ejected out of the nucleus is the alpha particle, which is a helium nucleus. You might also see this written with the alpha symbol, alpha 4, 2. An example of alpha decay happens when the radium-226 nucleus, which has an atomic number of 88, ejects a helium nucleus, or an alpha particle, helium-4, and turns into the radon nucleus, which has an atomic mass of 222 and 86 as an atomic number. In beta-negative decay, a neutron changes into a proton, and an electron and an antineutrino is ejected from the nucleus. So in our original parent nucleus, a neutron turns into a proton, and an electron and an antineutrino is ejected from the nucleus. The general equation for beta decay looks something like this. The original parent isotope, XAZ, turns into a daughter isotope, keeps the same atomic mass because we have the same number of nucleons. A neutron is just turned into a proton. But because now we have one more proton, the atomic number increases by 1. An electron is ejected from the nucleus, and because this new particle has been produced, an antiparticle must also be produced. So an antineutrino is also ejected from the nucleus. You might sometimes, instead of seeing an electron written, you might see the beta particle notation written, which is beta 0, negative 1. Iodine 131 is a good example of beta-negative decay. Iodine 131 has an atomic number of 53. When it decays in beta-negative, it turns into the xenon nucleus. It maintains the same atomic mass, 131, but increases its atomic number by 1 to 54 because a neutron is turned into a proton. Also produced is an electron and an antineutrino to balance it out. Beta-positive decay is similar to beta-negative decay, except for in beta-positive decay, a positron is produced instead of an electron. In beta-positive decay, a proton turns into a neutron, and a beta particle, which is a positron or an anti-electron, as well as a neutrino, are ejected from the nucleus. So in our original parent nucleus, a proton turns into a neutron, and a positron as well as a neutrino are ejected from the nucleus. The general equation for beta-positive decay looks like this. The original parent nucleus, XAZ, turns into the daughter nucleus, which is Y, has the same atomic mass, but it decreases by 1 proton, so it becomes Z minus 1. Ejected from the nucleus is a beta-positive particle, which is E0 plus 1, and a neutrino. Since the positron is antimatter, the neutrino that's ejected is regular matter. You might also see the positron written as a beta particle, beta 0 plus 1. Nitrogen-13 undergoes beta-positive decay. This is nitrogen-13 with the atomic number of 7. When it undergoes beta decay, it turns into carbon, maintains the same atomic mass, but the atomic number decreases by 1 because it has 1 less proton, and goes down to 6. Ejected from the nucleus is the positron, which is the anti-electron, and to balance it out, a regular neutrino is produced as well. Last, we have gamma radiation. Some of the energy released in the nuclear decay leaves the nucleus as kinetic energy of the ejected particles. But some of the energy remains, and some of the electrons surrounding the nucleus become excited. They're at a higher energy level. Here's a Bohr model for lithium. The lithium nucleus contains 4 neutrons and 3 protons. Surrounding lithium are 3 electrons, 1, 2 in the first energy level, and a third one in the second energy level. This is regular lithium, lithium 7, 3, in ground state. When lithium becomes excited, its electrons jump to higher energy levels. Here's a diagram of the lithium 7, 3 isotope as it's excited. We draw a star next to the symbol to indicate that the atom is in an excited state. After a while, the excited electrons fall back down into ground state, and gamma-ray photons are emitted as they fall. We can draw this in nuclear notation. We have the lithium 7, 3 atom when it's excited on one side of the equation, and as the electrons fall back down, it becomes regular lithium, lithium 7, 3, in ground state, and gamma-ray photons are emitted. You can calculate the energy released in radioactive decay. If you find the total mass of the parent isotopes for a nuclear decay and compare it to the total mass of the daughter isotopes, there will often be some missing mass. This mass has been converted into energy, which is released in the kinetic energy of the alpha and beta particles as well as gamma radiation. Here's an example. Calculate the energy released in the alpha decay of thorium-130. We can use the masses after we've determined the equation to determine the amount of missing mass and convert it into energy. The alpha decay looks like this. We start with thorium-230 with atomic number 90. As it decays, it releases an alpha particle, which is the helium nucleus, helium-4, 2. The atomic number decreases by 4, so we have a daughter isotope of 226, and an atomic number of 90 minus 2 is 88. This is radium, Ra. The mass of the parent isotopes is just the mass of thorium, which is 230.033134 atomic mass units. The mass of the daughter nuclei, or the mass of radium, 226.025410, plus the mass of the alpha particle, which is 4.002603, which gives us a total mass for the daughter nuclei equal to 230.028013. There's been a change of mass, which is the mass of the daughter nuclei minus the mass of the original parent nuclei, of negative 0.005121 atomic mass units. Or note the negative in this result means that mass has been lost. We can convert this mass into kilograms. The change in mass in kilograms is negative 0.005121 atomic mass units times 1.66 times 10 to the negative 27 kilograms per atomic mass unit. This gives us a change in mass equal to 8.50086 times 10 to the negative 30 kilograms. We use Einstein's equation, E equals mc squared, to convert this missing mass into energy. This is 8.50086 times 10 to the negative 30 kilograms times c squared, which is 3 times 10 to the 8 squared. This gives us an energy released equal to 7.65077 times 10 to the negative 13 joules. It's good to convert very small amounts of energy into electron volts. To do this, we divide by 1.6 times 10 to the negative 19 joules per electron volt, which gives us an energy equal to 4781733 electron volts, which is 4.78 mega electron volts. Exposure to high amounts of radiation can be quite hazardous. Ionizing radiation consists of particles that have sufficient energy to knock an electron out of an atom or molecule, thus forming an ion. A single alpha or beta particle has enough energy to ionize thousands of molecules. Nuclear radiation is potentially harmful to humans because the ionization it produces can significantly alter the structures of molecules within a living cell. Even sunlight contains enough ionizing radiation to affect your body and cause skin cancer. The risks of radiation exposure include burns, mutations in the DNA in your cells, which can be passed on to offspring, cancer, radiation sickness, and death. We'll look at each type of radiation and its relative danger, starting with alpha radiation. The mass of an alpha particle is 4.0026 atomic mass units. It travels with a relatively slow speed And because it's slow and quite massive, it can be stopped by something as thin as paper or your skin. So it doesn't actually penetrate that deeply into your body. But alpha particles have high ionization because they have a charge equal to 2 times the elementary charge, so they're quite high charged. Beta particles have negligible mass. They travel at very fast speeds, and they have slightly higher penetrating power than alpha particles. They can be stopped by thin metal, which means they can get more deeply into your skin, but not too very far into your body. They have medium ionization ability with their charge of 1 times the elementary charge. Gamma radiation has no mass because it's photons, and photons have no mass. They travel very, very fast, however, at the speed of light. And because they're traveling so fast and have no mass, they have high penetrating. Because they travel so fast and have no mass, they have high penetration power. You have to be protected by several centimeters of lead or concrete to block gamma radiation. Gamma radiation has very low ionization ability. However, because it has such high penetrating power, gamma radiation is the most dangerous. Next, we're going to talk about calculations involving radioactive decay rates. A stable nucleus is one that is much less likely to undergo radioactive decay. Uranium-238 is much more stable than uranium-235, which is lighter and more active. In order for a nucleus to be stable, there must be a balance between the number of protons and the number of neutrons in the nucleus. There are 106 naturally occurring atomic numbers, or elements, and 1,300 different proton-neutron combinations. These are the isotopes. This table shows you all the possible combinations for the first 16 atomic numbers. The black line indicates the stable proton-neutron combinations. For example, helium-4, 2 protons, 2 neutrons, is a stable nucleus. The gray isotopes are less stable. They would be more likely to be radioactive, and they would decay more quickly. The blue can't exist naturally. Because they're way too unstable. For example, you would never have helium with 2 protons and 21 neutrons. That won't happen. It'd be way too unstable. Different isotopes decay at different rates. Half-life is the amount of time it takes for half the nuclei in a sample to decay. The symbol we use for half-life is T1/2. So if this is the original sample of nuclei, after 1 half-life has passed, half of them will have decayed into the daughter nucleus. After 2 half-lives have passed, another half will have decayed and will have significantly less of the parent isotope remaining. After 3 half-lives have passed, the original parent nuclei will have been cut in half again. So if we started with 100% after 1 half-life, we end up with 50% of the parent nuclei remaining. After 2 half-lives, we end up with 25% of the parent nuclei remaining. And after 3 half-lives, it's cut in half again, and we get 12.5% remaining. The smaller the half-life, the more radioactive the isotope is. Here's 3 examples. Uranium-238 has a half-life of 4.5 billion years. Uranium-235, which is more radioactive, has a shorter half-life of 7 million years. That means if I had a rock of uranium-235, after 7 million years, half of it will have decayed. Carbon-14 has a very short half-life of 5,730 years. Radioactive decay is often shown through decay graphs. You can find the half-life from these radioactive decay curves by finding the halfway point, where half the nuclei have decayed, determining how long that took. So here we have 1 half-life, 1 T1/2. When that is decayed in half again, half of 50 is 25. 2 half-lives have passed. Cut that in half again at 12.5. 3 half-lives have passed, 3 T1/2s. The point where half the sample is decayed is the half-life. If we know the half-life of a particular isotope, there's a formula that we can use to calculate how much of the sample is left after a particular amount of time. The formula is N equals N naught times 1/2 to the power of small n, where capital letter N represents the amount of the isotope that is left after time has passed. This amount could either be the amount of mass, the percent that's left, the number of nuclei, or the rate of radioactive decay, which is given the unit becquerels. The unit becquerels measures the rate of radioactivity of the substance. N naught is the original amount. Small letter n, the exponent, represents the number of half-lives that have passed. You can calculate small letter n using the formula N equals T, the amount of time that has passed, divided by the time for 1 half-life. N equals T over T1/2. Here's an example. Polonium-210 has a half-life of 138 days. After 3.8 years, how much of a 765-gram sample of polonium-210 is left? The example gives us the original N value, which is 765 grams. We're looking for the amount left over after 3.8 years. We start by calculating the little n value. Little n equals the time passed divided by the time for 1 half-life. Time for 1 half-life is 138 days. The time that has passed is 3.8 years. To convert this into days, we multiply by 365 days in a year. This gives us 1,387 days. So small letter n equals 1,387 days divided by 138 days, which is 10.050724 half-lives have passed. Next, we use our formula to calculate the amount remaining. N equals N naught times 1/2 to the small n. This is 765 times 1/2 to the power of 10.050724. This gives us an amount left over equal to 0.72 grams. Here's another example. The half-life of a radioactive isotope is 6.8 years. If the activity of the original sample of this isotope was 4.9 times 10 to the 5 becquerel, what would its activity be after 100 years? So we're given a time of 100 years and a half-life of 6.8 years. The original amount of activity, our N naught value, is 4.9 times 10 to the 5 becquerels. N equals T over T1/2. So this is 100 divided by 6.8. This gives us 14.70588824 half-lives have passed. Now we can find out the activity level after 100 years. N equals N naught, 1/2 to the power of N. So N naught is the original activity rate, which is 4.9 times 10 to the 5 becquerels, times 1/2 to the power of 14.70588824. This gives us a value of 18 becquerels remaining after 100 years. Here's our final example. You have 75 grams of lead at the start of an experiment. How many half-lives have passed when 9.3 grams remain? So we're told N naught is 75 grams, and after some time has passed, we have 9.3 grams remaining. We're looking for the N value. So N equals N naught times 1/2 to little n. We start rearranging this for little n. N over N naught equals 1/2 to the n. To solve for an exponent, we need to use logarithms. If we take the log of either side, it will allow us to solve for small n. Log n over N naught equals log of 1/2 to the little n. When you're taking the log of anything with an exponent, that exponent can come out in front of the log. This is n log 1/2 equals log n over N naught. Now we can rearrange for little n. Little n equals log n over N naught divided by log 1/2. So we have log of 9.3 divided by 75 divided by log 1/2. This gives us N equals 3. So 3 half-lives have passed.